So we'll be continuing on with chapter 16, talking about acids and bases and acid-base chemistry. Uh, Last time we'd finished off talking about the pH scale, how it's derived, and how we can use the pH equations to determine the concentration of hydronium in a solution. What we'll be doing now is moving on to talking distinctly between how strong acids dissociate in a solution and how they react with water, and when you have a weak acid, when you dissolve that in water, and how it's going to react with water and its relative dissociation. So let's remind ourselves, for strong acids and strong bases, we can assume that the forward reaction is greatly favored over the reverse reaction. What that means is, if we look at our generic expression for strong acid reacting with water, is that we'd predict almost or over 99.9%, so nearly 100% dissociation. So when a strong acid is dissolved in water, we'd expect almost all the molecules to either be in the form of hydronium or the conjugate base. If we wrote out an equilibrium expression for this particular reaction, we would have something that looks like this down here. And specifically, we're going to call this the acid dissociation constant, or the Ka. It's exactly the same what we've been talking about before in terms of equilibrium constants, but now instead of K sub C, we're going to be dealing with K sub A, or Ka, which is the equilibrium dissociation constant of an acid. We have our products over reactants, so in this case our hydronium, multiplied by the concentration of our conjugate base, all of that divided by the concentration of the protonated acid. And as always, we're leaving out our pure liquids and pure solids from the mass action equation. So, like we're going back up to our first assumption, is this idea that Ka is very large. And where do we get that from? Because we're assuming 100% dissociation, or nearly 100% dissociation, you'd expect the equilibrium to lie very heavily to the product side, where we said over 99% of the acid is going to be in the form of hydronium and the deprotonated conjugate base, and a very, very, very small, so less than 0.1%, will be found in solution as the protonated acid. So in that case, large number in the numerator, tiny number in the denominator, Ka is going to be very large, on the order of, it could be up as well as big as 1,000,000, so 10 to the 6th, or stronger for strong acids. What this means is, though, we can use stoichiometry and limiting reagents to determine the final concentration of all species. So we're going to see now, we're going to go back to almost 1101 using stoichiometry, limiting reagents. That's going to be for dealing with strong acids, and we'll eventually get to strong bases. And a little bit of foreshadowing, when we get to weak acids and weak bases, we can no longer rely on this stoichiometry and limiting reagent, the simplicity of the problem, and we're going to have to fall back on using ice tables. But we'll deal with that when we get there. So let's start off here. So we'll start with an example. We have a solution of nitric acid, HNO3. It says, what is the pH of a 0.025 molar solution of nitric acid, right? So we're going to remember what pH is. pH is going to be our concentration of hydronium in solution, right? But right now I only know the concentration of HNO3. So let's take a look at our assumption about strong acids. So we have our reaction, chemical reaction up here. So HNO3 is going to react with water, and we're assuming essentially 100% dissociation. So the H will then be transferred to the water, forming hydronium in our nitrate anion. So since nitric acid is a strong acid, this is where we're going to be using our stoichiometry, is that it's assuming that all the HNO3, so that original 0.025 molar, is then converted into hydronium and nitrate. So that means the concentration of a strong acid, the hydronium, equals the concentration of the nitric acid, right? Because again, we're going to pretend we're omnipotent beings. We can pause time. We make our solution. Everything is HNO3 and it's dissolved in water. We unpause time. We let it react. When it's done, all of that 0.025 molar solution of HNO3 has now been almost entirely converted to hydronium and nitrate. And that is why we can make this assumption, and it's very reasonable, that the concentration of hydronium equaled the concentration of the HNO3 to start with. Based on that assumption, what we can do to find the pH, we remind ourselves that by definition, anytime I see P, I'll be using the function negative log. H is going to stand for the concentration of hydronium. At that point, we know hydronium is equal to the concentration of HNO3. HNO3 is equal to 0.025. Plug it in. pH of 1.6. We ask ourselves, does that make sense? An acid is going to be less than 7, and a pH of 1.6 would make sense for an acid. So let's try another problem. Same idea. This time we have a strong base though, right? So what is the pH of a 0.025 molar of NaOH? Right? So we want to recognize we have our metal hydroxide, so we know it's a base. So we're probably going to have to do a little bit more, maybe not legwork necessarily, but there's going to be a little bit more than just plug and chug for this one, because we're looking at the concentration of hydroxide at first, right? So let's take a look at what we got here. We assume sodium hydroxide, because it's a strong base, is going to fully dissociate. So essentially we had our 0.025 molar solution of sodium hydroxide. We're omnipotent, so we pause time and space, we let it go, and then we end up with 0.025 molar Na plus and 0.025 molar OH minus, right? We make that same assumption that we did with the nitric acid because of the strong acid. We'll do it with the strong base. So since NaOH is a strong base, the hydroxide concentration equals the original concentration of the NaOH, right? What I have down here is a rewriting of our Kw expression. So if you remember, Kw is 1 times 10 to the negative 14th, and that equals the concentration of hydronium multiplied by the concentration of hydroxide. So I've rearranged it so the concentration of hydronium equals Kw over the concentration of hydroxide. There's my Kw. There's my concentration of hydroxide. I've now directly solved for the concentration of hydronium. Since I did skip a couple of steps in these slides, it might be good that when you see me doing these examples, if things are skipping steps or maybe I'm going a little too fast, that you pause these videos as you go along and make sure you're writing out the actual steps to solve for these and not just writing down what I have on the slides, right? So now we've solved for the concentration of hydronium by knowing the concentration of hydroxide, right? We can plug that into our pH equation. So we have pH equals negative log of hydronium again. We plug in our concentration of hydronium. When the number we should get, 12.40, it's greater than 7, and that makes sense. And I'll also let you know there's several ways to solve this problem. You could have solved for POH first and then solved for pH from that. If you want to play around with the equations that we derived last week on Monday, be my guest. There's plenty of ways to solve this. This is just one of many. So that pretty much brings us to the end of strong acids, strong bases. It's just stoichiometry. It's just basically for this one, limiting reagents will come later when we look at reactions of strong acids and strong bases. So for the most part, strong acid, strong base, we're using stoichiometry. This is where it becomes a little bit more interesting when we're looking at pHs of weak acid solutions. So for this, we're just going to concentrate only on weak acids. Weak bases we'll deal with when we come back. But in general, the same principle applies. So you might see me drop in weak acids and weak bases, but the examples we'll do will focus on weak acids, right? So we go back to what we talked about before. For weak acids and bases, we expect similar rates for the forward and reverse reaction. Maybe not exactly, obviously we're not really expecting the same rates, but they're going to be in roughly the same orders of magnitude. So you're not going to get these extreme Ka values, right? So it's going to be small, somewhere near 1 or could 1,000, 10 to the negative third, in that air ballpark. We're not talking about millions or billions, right, for a Ka. So what this means now is we need to apply what we learned about equilibrium to determine the final concentration of all species. Before we used stoichiometry, now we're going to have to fall back on using ice tables. Just like with a strong acid and a strong base, right? So the strong acid we had Ka. When we write out the Ka for a weak acid, same expression. Concentration of hydronium multiplied by the concentration of the conjugate base, all divided by the protonated acid. So let's try this problem. It says the pH of a 0.250 molar hydrofluorous acid solution is 2.036. We're asked to find the values of Ka and pKa for hydrofluoric acid. The first thing you always want to start with, anytime you have a problem like this, is write out the chemical reaction. We know what's being dissolved in water, so we're going to immediately write down HF plus H2O. we know that it's an acid, so therefore the HF should, when you write it out, going to be its conjugate base, will just be F minus. The H has to go somewhere. The only option is to the water, and you write down hydronium. Right? So I will be expecting you to be comfortable if I just give you the acid and tell you that it's in water, that you'd be able to write an equation like this without me giving it to you. So once we have that equation written out, we can start to set up an ice table, right? So if we look in our I row, right, so our initial, we know we started with HF, and remember we're omnipotent beings, so we can pause time. You'll notice that I have not included anything for water. The reason for this, because remember in ice table, everything is in concentration and molarity. The same reason why we omitted water for the mass action equation, its concentration is its density. It's not going to change, right? So then we look onto the right-hand side. We here have our hydronium and our fluoride. Well, it's very easy to determine that we started with 0 molar fluoride, right? We're omnipotent beings. We pause time. All the fluoride's bound up in HF. There's none in solution at all. However, because we are dealing with water, remember the concentration of hydronium at 25 degrees Celsius is 10 to the negative 7th molar. It's still a concentration. But if we compare 10 to the negative 7th versus basically 2.5 times 10 to the negative 1, right, you're looking at 6 orders of magnitude or 1,000,000 times more concentrated the HF is over the H3O+. So we're going to approximate it as 0. And it usually is a pretty reasonable assumption unless the concentration of your acid is approaching low micromolar, high nanomolar level. We set up our change row, and we see that because we started with HF, and we started essentially with 0 hydronium and 0 F minus, we'll have to take from the HF, so the minus X, and then as that's consumed, we'll be producing, so plus X, hydronium, and plus F minus, all in a ratio of 1 to 1 to 1. And that's based off of the 1 to 1 to 1 molar ratio. Our final row is our E row. So we know at equilibrium, it will be 0.250 minus however much HF was consumed. And then we'll have the produced X amount of hydronium and X amount of F minus, right? So the nice thing is it gave us a pH, right? It said the pH was 2.036. So what I've gone here is I've already, again, like I said, I've skipped some steps, but I've rearranged the pH equation to directly solve for the concentration of hydronium, right? So remember, pH is negative log hydronium. When it's rearranged, hydronium you can directly solve for becomes 10 raised to the negative 2.036. And easy enough, way easier than what we've done in the past, we now have directly solved for x. We didn't have to do any quadratic equation. We know it's going to be 0.00920 molar. So now we're going to have enough information, we can plug into our Ka expression, and then we can directly solve for Ka, and then we can apply the negative log of that to solve for our pKa. So let's do that. The Ka specifically for hydrofluoric acid reacting with water is going to be hydronium times the conjugate base, so F minus, divided by the protonated HF. We saw that X before equaled 0.00920. We said that was equal to the high concentration of hydronium. It was also equal to the variable X, which is also equal to the concentration of fluoride. So right now we have the numerator all taken care of. Right? We also had an expression in our E row, where our equilibrium row, where it was for a concentration of HF, where it was 0.250 minus that value of X, so 0.250 minus 0.00920, and that gives us our final concentration of HF at equilibrium, which is 0.241 molar. We have all the information we need. We plug in our concentrations of hydronium, our concentrations of fluoride, and then divide that by the concentration of HF, again all at equilibrium, and our Ka for that is 3.51 times 10 to the negative 4th. We finish off the problem because it asks to also solve for pKa. We remind ourselves again that P is always the negative log of whatever follows it, so negative log of Ka, so negative log of 3.51 times 10 to the negative 4th is 3.455. Good. So let's do another problem. So calculate the pH of a 0.1 molar solution of hydrogen cyanide. At 25 degrees Celsius, it gave us the Ka at this point, right? So now we're doing a little bit differently. So in a sense, maybe not exactly working backwards, but we do need to get the pH from the Ka. In the last example, we were given the pH and solved for Ka. So we're going to do it a similar approach. We write down the reaction. We know HCN is, well, actually we weren't told it was an acid, right? If you're given a Ka, you can always assume that it's an acid, or at least write the expression in which hydrogen from that molecule is given to water, and which is what you see here. So the H from the HCN gets transferred to the H2O, and then that's going to form hydronium and the cyanide anion. Set up our ice table. Again, remember, for our I column, we're omnipotent, so we can stop time. We start with 0.1 molar HCN. Again, water doesn't matter because it's not in the mass action equation, and its concentration doesn't change. We'll make the assumption, at least reasonable at this point, that hydronium is approximately 0, even though in real life it's 10 to the negative 7th. Cyanide, again, the only way it could have got in the solution is if we added it, and since we only added HCN and we stopped time, there's no Cn minus in solution at all. Again, we set up our change row. So the only thing in there is hydrogen cyanide and water. So the hydrogen cyanide has to be consumed. It reacts with water to produce hydronium and cyanide. And that's why we have our subtracting X, or a certain amount of HCN is consumed by reacting with water to produce the equal amount of hydronium and cyanide. And then we have our equilibrium row. We know what the Ka expression is, products over reactants. We were also given the Ka. So what we do now is our Ka, that was given to us in the problem, 1.4 times 10 to the negative 9. Essentially, this is our concentration of hydronium, our concentration of cyanide, and this is going to be our, sorry, my cursor disappears sometimes, and this is going to be our concentration of HCN, right? All based off of our equilibrium, off of our ice tables. So now we have one equation, one unknown. Yes, it's 3 different x's, but they're all the same variable. We combine terms, so the x's become x squared, and we're left with this expression. We can rearrange. Sorry, I got a little bit messed up, but you know what that is. It's a quadratic equation. Plug it in. We're going to get 2 variables for x. One is negative, one is positive, right? Having a negative concentration doesn't make sense, so we choose the positive value. Now that we've solved directly for x, right? That means x is going to be equal to the concentration of hydronium. We don't even have to work. The question didn't ask us for the equilibrium concentration of HCN and Cn minus, just the pH, so we can forget those those columns. Just pay attention here. pH equals negative log concentration of hydronium. Plug it in, 4.92. It's less than 7, but it's kind of still high, right? So that's going to be our weak acid. So strong acids are usually around 0, 1, and 2 of a pH, and weak acids are like 3 to 6.9. So we're in that range of a weak acid, and that makes sense. So it's giving us a good sense that we're going in the right direction. All right. There's another way, and a simpler way we can go about this. Is the exact same problem we just looked at. There's another quicker way we can go about the last problem. I've set up everything exactly the same. This is exactly the same slide, actually. So we're here, right? There's our Ka expression. Before, we had to go through the trouble of doing the quadratic equation, right? It takes time. It's kind of annoying. An assumption we can make, but we're going to have to test later to make sure it's correct, is we can assume x is much, much, much smaller than 0.1, right? And we're getting that from the Ka. Because the Ka is so small, it's telling us that only a small amount of the product is favored. So that means not a lot of that HCN is going to convert to Cn minus. So we're going to assume that 0.10, that x is much, much smaller than the concentration of HCN, or 0.1. If we make that assumption, our equation simplifies to 1.4 times 10 to the negative 9th equals x squared over 0.1. Well, that's easy. Multiply both sides by 0.1, take the square root, and you're left with the concentration of hydronium at 1.2 times 10 to the negative 5th. Plug it in, 4.92. If we go back a couple of slides, 4.92 is what we solved using the quadratic equation. You cannot always use this method. We're going to come across examples where we can't, right? So it's exactly the same value we get as when solving with the quadratic equation, right? The way that you check for this is at the concentration of hydronium, right? This 1.2 times 10 to the negative fifth. If this first number here, this 1, which is essentially it's 0.000, hold on, 0001, right, is smaller than the last significant figure here, you would be 2 more decimal places out for the 1, which basically says that this number is so small compared to this, it's minuscule, then that this assumption was correct. And so that's how we're going to check our assumption. I'll do a couple more examples on Monday when we come back so we can see it, just so we have it under our belt. But you want to make sure that this number is smaller than this number to the point that it's not small, that it's basically beyond its significant figures is what we're looking for. So another thing that will happen when we're talking about weak acids, and it's a common way to talk about weak acids, is percent dissociation. It's pretty easy. It's exactly what it sounds like. It's the amount of HA that's dissociated, so the concentration of A minus, all over the concentration that you started with, multiplied by 100. One thing that you'll notice is that percent dissociation changes as concentration goes up. That's because you're dealing with an ice table, right? And that at low concentrations, you're also dealing with concentrations of the autoionization of water, so that 10 to the negative 7th concentration. So as you approach that, things get a little bit more complicated, but as you start to surpass that 10 to the negative 7th concentration, right, you end up being, your concentration is going to go down. So it's affected by the equilibrium of having both the autoionization of water and the percent dissociation of the weak acid. So let's answer this question. It says calculate the pH and percent dissociation for a solution of 0.033 molar HF. So it's a very low concentration, right? Where it's given to us that we have our balanced reaction, HF reacting with water to form hydronium and fluoride, and it gave us a Ka. So we approach it the same way with most weak acid dissociation problems. We're going to set up our ice table. So again, I've walked you through before. I think everyone's familiar with what I'm doing here. But I've set up my ice table. I see that I started with 0.033 molar HF. Again, water we don't care about. We're making our assumption about hydronium. That's approximately 0. And we know fluoride equals 0. We see that the only way to make hydronium and fluoride is to consume HF. And then we're left with our equilibrium concentrations. Set up our Ka. We know what the Ka is equal to, so now we're left with this expression. And what we'll do first is we're going to make our assumption. Our assumption, again, is that the amount dissociated from the HF is so small that essentially this concentration of HF remains constant. Right? So that was our first reasonable assumption. We saw in our last hydrogen cyanide example that yes, it was quite small, the percent dissociation, so it was a reasonable assumption. But let's go ahead with this. So we assume that the concentration of hydronium and fluoride is much, much, much less than 0.033. We can solve for x. And we end up with the concentration of HF, which is 0.033 minus x. So the final concentration of HF is 0.030. We check our assumption. Take a look here, right? When we subtracted this number from the 0.33, it didn't leave us with 0.033. In fact, it's 0.030, right? This number was so if we look here, this 3 is right here. If we wrote this out so what I would have you do if you're confused, take this 3.4 times 10 to the negative third, write it out in standard notation as 0.0034. And then you can see here 0.0034. Your last significant figure here is the 3 that's here. So it's this is too large. We now can't use this assumption. When this assumption is broken, that means we have to use the quadratic equation. We go ahead, we do it the long way. We get a negative value and a positive value. Our only plausible value is the positive one. Plug it in. We know our concentration of X, fluoride and hydronium equal X. Concentration of HF, we already solved for. So percent dissociation is going to be the concentration of HA dissociated divided by HA initial. Well, HA dissociated is going to be equal to X, because that's how much came off, so dissociated. And we started with 0.033. So there we go. There's my percent dissociated, 0.0033, divided by how much I started with, 0.033. So it's a 10% dissociated solution. And actually, that brings us to the end of our lecture. So we got through it 25 minutes. Hopefully it wasn't too long, but we're caught up with the syllabus now. What I'll probably do when we come in on Monday, I'll do one quick example of these on the board just so we can do it together. But I would recommend, if you had either any trouble following this or things went a little bit too quick, I'd go back, give it a watch again, and make sure you're doing all the math out by hand. Don't just be watching passively as I do it. Make sure that you can do the math and that you're comfortable doing the math. Alright, so that's it. I will see you all on Monday.